Yeah, it does. All right, so welcome back to research. Today we're going to be talking about SDR stuff. It's really cool and a lot of fun. So I'm Ian. I'm the head of research and mentorship. I'm a fourth year, Jesus, and this is my last semester. Yikes! I just accepted an offer with SRA to be a pen tester, so I'm super excited. I'm going to be staying here in Rochester, so I get to annoy you guys all the time next year. And I really like being outside and planes and stuff, which comes in a little bit later. So software-defined radios, for those of you guys that aren't familiar with them, are radios that take a lot of the things that were traditionally implemented in hardware and reduce them down into things that are implemented in software. So this is the one I got for Christmas. It's really cool. It's an AirSpy R2. It's this big, and it does a lot of things, which we're going to talk about. The official definition is software-defined radio is a radio communication system where components that have been traditionally implemented in software or in hardware, all the different parts there, are instead moved to software. And that's pulled straight from Wikipedia. So like I mentioned, it moves a lot of the hardware into software. This means it offers a lot of flexibility, and it's a really easy way to get into the world of radio. This is actually a RTL SDR, which is a DVB-T dongle. This is a USB dongle that can be plugged into your computer, and it was originally designed to receive over-the-air TV and TV signals. How back before cable TV, they broadcasted out over the air, and yeah, they still do. But this was back when cable was like the premium thing, and they didn't have commercials. So that's why this was free. And then cable just said, nah, we want more money, and then implemented commercials. But the cool thing about this is that with a certain antenna and some hardware hacking and a little bit of just kind of looking around at it, you can use this to receive over-the-air signals outside of that TV spectrum. A lot of it can be done with a $20 dongle, which we're going to talk about. So SDR started back originally in the 70s, and then it was designed by E-Systems, Inc., and it didn't really get fleshed out until the 80s and 90s. E-Systems later became Raytheon, but it was originally designed for the DoD, and it kind of pivoted a little bit once it became a mainstream product and people started using it and going, oh, hey, this has a couple more applications other than planes and stuff. While E-Systems was doing it, Joe Matola also was working separately on his own implementations. He was originally trying to build a GSM base station, and that's part of the technology that worked with older cell phones. And eventually the two kind of crashed into each other, and the Air Force ended up buying the E-Systems one and forbid Joe from actually publishing the research he did and stuff like that until a little bit later. So that was kind of cool because it was two independent ideas that ended up resulting in almost the same thing with just a couple implementation differences. After it was released, in air quotes, the Air Force was like, yeah, okay, you can publish that now as long as you don't publish the specific implementation that we're using for these certain use cases. That takes us down into the Speakeasy project. Speakeasy Phase 1 was a way for the Air Force to build a multi-faceted communications network between planes, troops on the ground, Navy ships, and satellite constellations. The first one sucked pretty bad. It had a whole bunch of issues. The crypto chips couldn't talk to each other and couldn't hop frequencies fast enough. It crashed and locked up all the time. And the filtering on it sucked really bad. So that launched Speakeasy 2. This started as, one, a way to fix all the other problems, and then build a solution that was lighter weight, more effective, and that didn't break all the time. They did this in 15 months out of a 3-year development cycle and crushed it. It was also the first use of FPGAs for radio stuff. So this is kind of a diagram on how radios work. Up top is a traditional one where you have a whole bunch of stuff implemented in hardware, and then after that you have the software. But when you move down to an SDR, it reduces the number of components and brings out a couple specific things. So you've got your amplifier and filter, which are both hardware, and then your analog to digital converter and digital digital to analog converter. So analog to digital takes analog and converts to digital, and digital back to analog. Then you've got all of the other stuff, which is implemented software. Everything past this point. And that took this chunk and it spread it out all the way through here, while still covering a bunch of stuff up there. This makes it really powerful and really flexible. So there's a ton of different things that you can do with SDRs. You can receive FM radio. You can snoop on conference speakers. You can listen to hams talk. You can capture satellite TV stuff, not the direct TV kind of satellite stuff, but a couple other things which I'll talk about. You can receive stuff from the ISS, which is really cool. They only broadcast on specific occasions, which I'm going to talk about in a sec, but you're still receiving images from the astronauts that are just kind of throwing it back down to Earth, which is, in my opinion, really cool. And lastly, well, not really lastly, but another one of the things you can do is you can listen to other public radio frequencies. And one of those is the Rochester Airport. I was hanging out with my SDR last night, and I was listening to the controllers talk to planes as they were coming in. So there's a lot of common software that goes with SDRs. One of the most common ones is SDR Sharp, and that's what I'm going to show you guys in a little bit. You can also use GNU Radio, GQRX, and a ton of other ones. Those are just some of the most popular ones. I have an AirSpy radio, and with that, they offer a software package which has a ton of different stuff included in it. One of the things is ADS-B Spy, which we're going to get into. There's also AstroSpy if you're looking out at satellite stuff. Spectrum Spy, which gives you a big overview of the actual radio frequency map and everything that goes along with it. And then there's Spy Server, which lets you run in kind of a headless mode. So you throw that on a Raspberry Pi, plug the antenna in, and you're off to the races. So this is SDR Sharp, and I'm just going to blow that up a little bit. There's a lot going on here. So on the left, you've got just a bunch of settings. Up here, you have your frequency graph overall. Here you've got your waterfall, and then this is the IF spectrum. So this is showing this expanded out. So the waterfall shows wherever you have big peaks in signal, and this part up here shows those actual peaks in the current form. This is like a historical view. These are all just FM stations because it was a really easy thing to pick off. What I was listening to at this point was 96.5, which you can tell from the digital signals broadcasted along is Rochester's classic rock station. Some of the stations work like that. That's how when your car displays something, like the actual station name or whatever music's playing, it comes in that block right there. So that's broadcasted along with the FM radio signals. This is an image that was received from the ISS. This one was specifically for the ARIS 20th anniversary. And it was received with this antenna over here. Pulled this up from the amateur radio subreddit or the RTL SDR subreddit. Either way, this one was really cool. And one of my goals eventually is to be able to pick up the satellite stuff. Yeah. You can also pick up some of the weather radar ones. So this was from a NOAA weather radar satellite. And there are a ton of really cool images of people picking up hurricanes and stuff like that when they're still out over the oceans. And then this one is one of the actual imaging satellites. And there are a ton of beautiful, like high-definition pictures of Earth that you can just pull from the satellites as they're going around. And a lot of them are in geosynchronous orbit, which means that they stick above the same spot-ish. So you can get really clear, repeated images of the same type of thing. Nope, wrong way. So there are a ton of different antennas you can have with an SDR. I have two of them right here, my tiny little one and then one that expands a little bit. But both of these are pretty like entry-level antennas. This is an antenna made out of slinkies that somebody put up in their attic. You take two metal slinkies, solder them up with the right connectors, throw a coax cable on it, plug it in, and then you've got an antenna. This one somebody's using to receive trunk signals, which are the things that typically law enforcement use for their radios. So if they're not encrypted communications, but it's still a trunk system, you can pull all those signals in, and they've got a ton of different dongles down here to receive different parts of the spectrum. And that's how people would listen to things like the Monroe County Sheriff's or whatever law enforcement agency is near you. And that's a big old satellite that used to be used for, not a dish, that used to be used to receive TV signals. Now somebody has it hooked up to receive a lot of various communications. So this one's made out of tape measures, which is really cool because you can make antennas out of almost anything. Also, the reason that I have a metal baking dish up here, but we'll get to that. And this one was just a meme about how my life is going to be in the future, because I already have 2 and it's only been a week and a half. So TLDR on antenna, or using an SDR, plug in your antenna, install the software, set everything up, launch the program, and you're good to go. It's super easy to get into. Sure, there's going to be some config tweaks and stuff like that, but for the most part, it's pretty easy. And just because we're a little short on time, I'm going to skip, wrong direction again, this one. But now for the fun stuff. So one of the projects I'm doing with my SDR is ADSB monitoring. ADSB is automatic dependent surveillance broadcast. And that sounds real sketch, but what it is it's a way for planes to talk to each other and to base stations in order to figure out where they are and, in the end of things, make sure they don't hit each other. There are transmitters and receivers at towers, base stations, aircraft, and satellites. And it's mandatory in most US aircraft as of 2020. So starting 17 days ago, you had to have this on your plane if you were in the majority of aviation. There are some exceptions carved out for experimentals and planes that are only going to meet certain criteria, but not going to see that too commonly. As a bonus, it carries weather information, which is FISB. That's flight information. So that tells the aircraft, hey, there's going to be a big storm up on the path. You might want to route around that or something like that. And then there's TISB, which is the Traffic Information Service. And this is an FAA service in the USA only that carries information for the non-ADSB aircraft. So this means that if your aircraft doesn't have a transponder, the FAA can still receive the position information with the radar system that we have currently and broadcast that out to planes that do to further that anti-collision. So most ADSB is carried on 1,090 megahertz. There's a second frequency at 978. And the FAA recommends using that if you're below 18,000 feet or flight level 18, or no, flight level 6, because it reduces the congestion on that 1,090 megahertz band. And with the number of aircraft that are out, that can cause some issues, so that's why they recommend the second. So this is just kind of an overview of how ADSB works. You have planes which talk to each other, which makes sure they don't hit each other. Planes that talk to the ground, which is how the controllers can figure out where the planes are and appropriately route them when they're, say, coming into an airport to land. You have planes that are talking to the communication satellites over there. And that's how, if you're, say, over the poles or over the middle of the ocean, you're still going to get information on the flight. There are 2 components to the ADSB system. You have an antenna on the plane, which is going to broadcast and receive ADSB stuff. And then you have a GPS system. The GPS system can either be GPS or the other equivalent substitutes for it, as long as you're getting accurate position information. So you can't do it with cellular or something like that. That all ties together to give a lot of information to the controllers, which makes sure planes don't crash. And we're going to skip that one because it's time. This is kind of the coverage map of the US of ADSB. So all of the East Coast is covered out into the ocean. Most of the Midwest is covered, and central US. And then you get out to the other coast where you've got a whole lot of other coverage. In Hawaii, you don't have much, and Alaska, where you've got populated areas, you have some. But outside of that, not much. The important thing is that this is just base station antennas. So this is things on the ground that are able to receive the signals. So my setup, like I mentioned, is an AirSpy R2, a really cheap Amazon ADSB antenna, a Raspberry Pi 3, my laptop, and then a handful of software. So the software I'm going to be using in the demo is called ADSB Spy, and that receives these ADSB signals from planes on that 1,090 megahertz band. and ships them up into nice packages and ships them over to virtual radar server. Virtual radar server looks like this, and it takes planes and plots them on a map. So these are actual planes that were out above Rochester yesterday. I can't remember when this was taken. But these are all planes that are actually in the air at the time. When I was setting up to test stuff, I saw a plane fly north towards the Rochester airport, saw it on my map, and then actually figured out when it touched down just because of the fact that I could see it. So that was really cool, and as a big plane geek, I really like to see that kind of stuff. So with ADSB, you're going to get a lot of different information. You get all of this stuff comes from the ADSB. So you get air pressure, altitude type, the bearing of the flight, where the plane is actually flying, manufacturer information, and a lat long. So this allows you to plot it both horizontally and vertically in 3 dimensions. And then with an internet lookup from the tail number or call sign, you can figure out what the actual aircraft is doing, because there are a ton of services out there that offer similar things. A couple interesting finds I found. I found a CVS plane. I found a plane for Prime Air, which is the Amazon shipping service. Oh, they've got a huge fleet of planes. Yeah, that's no, they still use USPS, FedEx, and UPS, but yes, yeah. Prime shipping is black magic. I'm convinced. We ordered a basketball hoop. It showed up at my house 2 days later. Yeah, it's insane, but yeah, like that as an actual basketball hoop. It was really cool. So another one of the things I found was yeah. That's like actually how that works though, warehouses. So another one of the things I found was a Air Force KC-135. So this is one of the big air refueling planes. Yeah. This was really cool because my dad actually used to fly these. So I was able to spot one, and I sent him a picture of it, and he was like, oh, cool. And based off the altitude it was at and its actual heading, we figured out that it was doing air refueling for other aircraft at the time I spotted it. I actually spotted it out over Canada near Buffalo, and that's where this one happened to be based. I also today spotted I think it was a C-17 at the same time, which is an even bigger boy. Those are huge. Yeah. So a couple more interesting things. I've found planes from China, Hong Kong, Taiwan, the Philippines, Portugal, Qatar, Switzerland, the UK, Canada. This one's actually a Disney plane. WestJet, you can like rent planes and stuff. So this one has a Disney livery. You can see Mickey out on the tail of the plane. So that was really cool. And what's my end game? Sorry, wrong end game. Eventually, I'm going to build a planar disk antenna, which is one of these. It's like a super cheap antenna that outperforms a lot of other ones at any price point, probably below $100. One of the best antennas to build for indoor, where your setup is probably going to move a little bit, and offers a good amount of flexibility when trying to receive signals on different wavelengths. I want to learn more about how the physics behind this stuff actually work, because right now I'm kind of stumbling my way through and learning as I go. But actually thinking about it and learning would probably be good and going to help when I come back and talk more about this and the things I've found. I want to get my ham license eventually, and I want to... Oh, God. That means lots of studying. $300 questions? That's what we're talking about. All right. Yeah, well, we'll talk about that later on. So moving on, these are a couple SDR resources. When I post the slide deck, you guys will actually be able to click on these. This one's a really cool lab that one of the professors at a different college designed. I can't remember where it was, but it was a cool lab that I pulled a bunch of information from. This is the Wikipedia page. There are a bunch of subreddits. This one is a SDR that you can use on the internet. You can go to the website that I linked and from there, you can tune an SDR somebody has set up. I think in the Netherlands. I'm not positive. Yeah. And then I linked the basic $21 dongle you can get on Amazon to do SDR things. So with that, we're going to jump into demo. Simon, question? Yes, I did.
Did you want to pick up the stream?
Yeah, we'll cut it here. So thanks for coming out on the stream. This is going to be the last bit because I don't want to dox anybody, and then Shannon's presentation isn't going to be streamed. So thanks for tuning in. We'll see you guys around.